Okay, so in this lecture, I'm going to talk more about sets. I'm going to spend the first half of the lecture talking about some algebra of sets, and then the second part we'll talk about truth tables and cardinality, and I'll explain what those are. So I'm going to start off with some definitions. So these will be definitions. And they're going to be definitions of the union and intersection of sets. So given some subsets A and B of a set S, we're going to define a few different things. So the first one is going to be the union. And I expect some of you have seen this before. So this is written as A union B. So that is the set of all x that are in S such that x are in A or x is in B. Okay, so let's just take an example. So if S is the set of all students at Oxford, and A is the set of all students studying maths, and B is the set of all students who are in my college, then A union B is the set of all students who are either studying maths or who are in my college. It's basically the set of all the students who I ever meet. We also have the intersection. So that's A intersect B. That is the set of all x in S such that x is in A and x is in B. So in that example, that would be the set of all students studying maths in my college. So those are the students who can't get away from me. Okay, we also have the complement. This is just of one of the sets, so I'll call this AC. That is the set of all x that are in S, but that are not in A. So not... Oops. I'll write that bit better. X is not in A. Okay, so in that example, that would be the set of all students in Oxford who are not studying maths. They don't know what they're missing out on. Okay, then we have the set difference. Which is A backslash B. That is the set of all x which are in A. In fact, maybe I should have just written it as x is in A. X is in A, but not in B. Okay, so in that example, that would be the set of all students who are studying maths but are not in my college. You may have seen the Venn diagram as nice ways of drawing some of these, and I find that quite useful. So if A and B are the regions inside those two circles, then A union B, for example, would be that region there. A intersect B would be like that region there. The complement of A, if A is the left-hand circle, or the region inside the left-hand circle, then it would be the region outside of that. And A but not B would be the sort of moon-shaped region there. Okay, so if the subsets were subsets of R2, then these diagrams could be literal illustrations of the set. But more generally, it's quite common to use to draw pictures like this. And obviously, because we work on a piece of paper, and we're working in R2 or in a subset of R2. But even if the sets are something else, it can be quite useful to draw pictures like this. Another thing I want to define, which is quite straightforward, is what it means to say that two sets are disjoint. So I'll say two sets are disjoint if they don't intersect. So if their intersection is empty, so A intersect B is the empty set. You can also take unions and intersections of more than two sets, obviously. So if I have a family of sets, which I'll write like this. So if AI, inside curly brackets, is a family of subsets, it's indexed by the I, so that I would be a member of some indexing set, capital I, which very often will be a subset of the natural numbers, but it doesn't have to be. Then we can take the union and intersection of that family. So we draw that as a big union sign over I in I of the AI. So that would be the set of all x in S such that x is in AI for some I. So when we say for some, we mean for at least one. And then we could take the intersection of the AI. That would be the set of all x in S such that x is in AI for all I. Okay, so that's unions and intersections. What I now want to do is to prove a few things. So I'm going to first of all prove what's a fairly obvious proposition, but turns out to be quite useful. This is something called double inclusion. And so we're going to take two sets, A and B, and the statement, the proposition, is that A equals B if and only if A is a subset of B and B is a subset of A. So that hopefully seems reasonably obvious, and we're going to prove it. This turns out to be quite a useful sort of recipe for how to show that two sets are the same. This form of statement, something, if and only if something else, is something you see all the time. If and only if is a phrase that you'll keep coming across. What it means is that if this is true, then this is true, and if this is true, then this is true. And that indicates how you should go about proving a statement like this. First of all, suppose that one side is true, show the other side, and then flip it around and say, suppose that the other side is true, and show the first side. So that's the way that we're going to prove it. In this case, the proof is quite straightforward. It's almost one of these ones that's too straightforward to work out what to actually write down. So first of all, we're going to suppose that the left-hand side is true. So we're going to suppose that A equals B. So A equals B if all the elements of A and B are the same. That means that any element of A must be an element of B. And that is exactly the definition that for A being a subset of B. So I'm going to say then every element of A is an element of B, and that means that A is a subset of B. And I could have written that the other way around. I could have said, so rather than writing this, I could have written then every element of B is an element of A, because A equals B could be written that way too. And then that would be the definition of B being a subset of A. But I don't need to bother, since the argument is exactly the same, I don't need to bother writing it out again. I'm just going to write similarly B is a subset of A. Okay, if you have an identical argument being repeated, we don't tend to repeat it. That's kind of, well, it's just a waste of space. Okay, so that shows that if A equals B, then A is a subset of B and B is a subset of A. So now we're going to go the other way around. So I'm going to write conversely, suppose that A is a subset of B and B is a subset of A. Okay, and we're trying to show now that A is equal to B. So we need to try and show that this means that all the elements of A and B are the same. So I'm going to say for any x, I guess I haven't really said this, but so these A and B are really subsets of some larger set S. So let's let A and B be subsets of some S. So I want to say for any x in S, if x is in A, then since A is a subset of B, that means x is in B. So then since A is a subset of B, x is in B. So any element that's in A is in B. And then I want to show that if any element that's not in A is not in B, because then that would mean that all the elements of A and B are the same. So for any x in S, either x is in A or it's not. So if x is in A, then we've shown that it's in B. If x is not in A, then it can't be in B because B is a subset of A. So since B is a subset of A, if it was in B, then it wouldn't be in A. If it was in B, then it would be in A, but it isn't in A. So I'm going to say then, since B is a subset of A, x is not in B. And so if x is in A, x is in B, and if x is not in A, x is not in B. So I'll say, so the elements of A and B are the same, i.e. A is equal to B. Okay, and that concludes the proof, because we've shown that if we start now with the right hand side, then it means that we have the left hand side. But I was wanting to point out that when you have to prove something like this, really try and separate it out into sort of two different directions. So here I was trying to make that clear by saying, suppose the left hand side is true, and then we come to the conclusion that the right hand side is true. And then we said conversely, which is a good way of saying now we're going to go the other way around. Conversely, suppose that the right hand side is true, and then we try to arrive at the left hand side. Okay, so as I said, this is useful as a way of proving that two sets are equal, and we're going to see that in the next result. So this is going to be another proposition. This is going to be the distributive laws for set unions and intersections. So this time we're going to let A and B and C be some subsets of a set S. And then the claim is that A union B intersect C is the same as A union B intersect A union C. It's kind of telling me that I can expand the brackets. That's what distributive means. And the second law is that A intersect B union C, this is just the other way around, is the same as A intersect B union A intersect C. Okay, you can think of these actually in terms of a Venn diagram as well. If this is A, B and C, then that first set is A union B intersect C, which is this region here. And the distributive law is kind of telling us that we can think of that set in two different ways, either as the union of A and B intersect C, or as the intersection of A union B and A union C. And you can think about that in terms of the diagram. So let's prove this. I'm only going to prove the first one actually. I'm going to leave the second one for you. So we're going to try and show that the left hand side here is a subset of the right hand side, and then we're going to show that the right hand side is a subset of the left hand side, and that will show that they're the same set. Okay, so first of all I'm going to suppose that I have an x which is in the left hand side, and then try and show that it's in the right hand side. So if x is in the left hand side, it means x is in A, or x is in B and x is in C. So I'm going to say then x is in A, or x is in B and x is in C. I'm using brackets just to clarify how that sentence works. Okay. Now in either of these cases, if x is in A, then certainly it's in A union B, and it's also in A union C. So if we're in this case, then we are certainly in the intersection of those two sets. If we're in this case, that x is in B and x is in C, then for different reasons x is in A union B and it's in A union C, because of being in B and C. So again, it will be in the intersection. So it will be in the right hand side. So I want to write out something to explain that. So I'm going to say in either case, x is going to be in A union B and x is going to be in A union C. So x is in the right hand side, i.e. the left hand side is a subset of the right hand side. Okay, now we're going to go the other way around. So we're going to say conversely, suppose x is in the right hand side. So x is in this set here. So then I'll write then x is in A union B and x is in A union C. And so in order for x to be in A union B, there are two ways that could happen. X could be in A or x could be in B. If x is in A, then it's automatically in here. So that's one option. If x is not in A, then it must be in B in order for this to hold. And in order for this to hold, it must be in C. So there are two cases. Either x is in A, or I'll say if x is not in A, then x is in B and x is in C. So in that second case, x is in the intersection of B and C. So I'll say, and therefore x is in the intersection of B and C. And it could be in all of these things, but either it's in A, or if it's not in A, then it must be in the intersection of B and C. And that exactly means that it must be in the union of A and B intersects C. So I'll say, hence, x is in A union B intersects C, which is the left-hand side. So we've shown that the right-hand side is a subset of the left-hand side. I'll say, so left-hand side is a subset of the right-hand side. Okay, then we bring those together. I'll say, hence, by double inclusion, the left-hand side and the right-hand side are equal. Okay, so there was a similar kind of argument where it's helpful to split it up into two separate bits. I want to show one more proposition, and this is quite an important one, about how complements of unions and intersections work, and this is called De Morgan's laws. So this time we're just going to need two subsets, so let A and B be subsets of S. Then we have two things. First of all, the complement of the union, A union B, is the intersection of the complement of A and the complement of B. And secondly, the other way around, the complement of the intersection is the union of the complements. So this is kind of telling you that you could take the complement through the brackets, provided that you change the union into an intersection and the intersection into a union. So this is quite an important rule. So let's try and prove it. And again, I'm only going to prove the first one. And we're going to do the same method. So we're going to try and show that the left-hand side is equal to the right-hand side by showing that they're subsets of each other. So first, let's suppose that x is in the left-hand side, so it's in the complement of A union B. That means that x is not in A union B, so it means that x is in neither A nor B. So I'll write that as then x is not in either A or B. But that means that x is in the complement of A and it's in the complement of B. So x being not being in A is equivalent to saying x is in the complement of A, and x not being in B is equivalent to saying x is in the complement of B. And therefore it's in the intersection of the complement of A and the complement of B, because it's in both of them. So x is in A complement intersect B complement. Then we go the other way around. So now I say, conversely, suppose that x were in the complement of A intersect complement of B. So then that means that x is not in A because it's in the complement, and it's not in B because it's in the complement of B. So x is in neither A nor B, and that means that x is not in the union of A and B. So it's not in either A or B. Then it means it's not in A union B. So I'm going to say x is not in A union B, i.e. x is in the complement of that. So I'm just going to conclude then by saying, by double inclusion, the left-hand side A union B complement is the same as the right-hand side A complement intersect B complement. Okay, and as I say, I'll leave the second one for you to have a go at, following basically a very similar argument. Okay, so these are quite important laws, and they apply even if we have unions and intersections of more than two sets. So I'll just say here that De Morgan's laws extend to families of sets. So if I take a union of some AIs, for i's in an indexing set, and then I take the complement of that set, that is the same as the intersection of the individual complements. And the other way around, if I have the intersection of all the AIs and I take the complement of that, that is the same as the union of the individual complements. Okay, so you'll make a lot of use of these laws. Okay, let me summarize what we've done there. So we've defined unions and intersections, and we've seen how Venn diagrams can be a helpful way of illustrating those. we've looked at the double inclusion principle and seen that that's a useful way of showing that two sets are equal, and we've used that to prove the distributive laws and then to prove De Morgan's laws. So the next thing that we're going to look at is going to be truth tables, and these provide an alternative way of proving some of the things that we've just been looking at. So these are truth tables, and I'll say these provide an alternative method for proving set identities, I'll say. Okay, so how do these work? So we're going to make a table, and in the header of the table I'm going to list some sets, and I'm going to just do two sets to make this slightly easier. And so the way that this works is that we're going to try and catalogue all of the possible cases for whether a given element is in each of these sets or not. And if I work with two sets, then there are going to be four possibilities, because for each set we could either be in or out of it. So I'm going to fill in a bit more of this table in a second, but let me just explain how it's going to work. So we're going to put in a T or an F for true or false in the table to catalogue the different cases of whether a given element is in or out of each set. And the columns are going to correspond to different sets. So with two sets, there's going to be four possibilities, as I said. So we could be not in either A or B, in which case we put F and F. We could not be in A, but we could be in B. Or we could be in A, but not in B. Or we could be in both of them. And that's the four possibilities. Okay, but then what we do is we can then construct other sets. So for instance, we could look at A union B and make another column in the table. And then we just fill it in according to whether in each case we would be in that set. So in the first case, that's the first row, we're not in either A or B, and therefore we're not in the union of A and B. In the second case, we are in B, and therefore we're in the union. So we would be in the union in that case. And similarly, in the third and fourth cases, we would be in the union. Okay, so that's how it works. Let's see how we can use that to prove something. Let's prove the De Morgan's laws again. So we can use this to prove De Morgan's laws. And let's prove the one that we didn't prove last time. So I think that was that the complement of the intersection of two sets is the same as the union of their complements. So we want to try and show that those two sets are equal to each other. So we're going to do that by building a table. And the first part of the table is going to look identical to the one I've already drawn. But then we're going to make the table a bit longer, because I'm going to be interested in various other sets. So we're going to first of all have A and B, and I'm going to catalogue those different cases again. So we'll have not in either of them, in B, in A, or in both of them. And then I want to be interested in ultimately finding out whether we're in or out of this set and this set. And the idea is that we want to try and show that these two sets are the same, which we're going to do by showing that the columns of this table are the same. So I'm going to do this in stages. So let's first of all work out A intersect B. And then we're going to work out the complement of that. You don't need to write out the sort of sub-stages here if you don't want to. But then we're going to be interested in the complement of A. We're going to be interested in the complement of B. And then we're going to be interested in the union of those two. Okay, So it would have helped if I knew what size the table was to start with. Okay, and then now for each case, I'm going to go across, filling it in. So if we're not in A and we're not in B, then we're certainly not in the intersection of A and B, and therefore we are in the complement of that. If we're not in A, then we are in the complement of A, and we are in the complement of B because we're not in B, and therefore we are in the union of those two. Okay, in the second case, we're not in A, and therefore we're not in the intersection of A and B, therefore we are in the complement of that. We're not in A, and therefore we are in the complement of A, but we are in B, so we're not in the complement of B, sorry. And therefore we are in the union of the two complements. Okay, and then we just keep going. So in the third case, we're still not in the intersection, therefore we are in its complement. This time we're not in the complement of A, but we are in the complement of B, and therefore we are still in the union of those two complements. And in the last case, we are in the intersection of A and B, and therefore we're not in the complement. And this time we're not in either of the complement of A or the complement of B, and therefore we're not in the union of those two complements. Okay, and the point here is that this column and this column are the same. So I'll say the fact that these two columns are the same shows that these two sets are equal. Okay, and so that proves this law here. Okay, so that's truth tables. The next thing I want to talk about is cardinality of a set, which is a measure of a set's size. And I'm going to talk just about finite sets, although I'll say a word about infinite sets. And this is going to turn out to be much easier to define once we have the idea of a bijection, which is what I'm going to talk about in, I think, 2 lectures' time. And so I'll come back to cardinality later on. But I want to give you something to work with, partly so that you can do a question on the problem sheet, and partly so that you give you practice at dealing with a slightly more awkward definition. So we're going to look at a recursive definition for the cardinality of a finite set. At the same time, this definition is actually going to give a definition of what it means to be a finite set. And in the end, the definition is simply going to be that the cardinality is the number of elements in the set. But we need to explain what exactly that means. So we're going to have a definition. So this is going to be a definition of finiteness and the cardinality for finite sets. Okay, and the definition may seem slightly peculiar to start with, but then hopefully once you've thought about it for a while it will make sense. So it's going to be a recursive definition. So we're going to start off by saying that the empty set is finite and has cardinality, which we denote with kind of modulus signs around the set, 0. So the empty set has cardinality 0. The empty set, remember, is a set with no elements. And then for any other set, I'm going to call it S. Set S is finite and has cardinality equal to n plus 1 if there exists an element which I'll call little s in S, such that if we get rid of that element from the set, so I'm going to write that as the set difference between the set S and the set that contains just that single element S, so such that the cardinality of that set is n for some n in the natural numbers. Okay, So a set S is finite with cardinality n plus 1 if there exists an element such that getting rid of that element leaves us with a set that has cardinality n. If that's not the case, so if it's not possible to get rid of an element and be left with something that has cardinality that's a natural number, then the set is infinite. So I'll say otherwise the set S is said to be infinite. Okay, so as I said, you may find that definition slightly peculiar, but if you think through it, it is really saying that the cardinality is the number of distinct elements in the set. So I'm going to say here that it follows that the cardinality of S is the number of distinct elements in S, if S is finite. Right? So you might think, well, why did we not just use that as our definition of the cardinality? But if you think about it, that effectively is what we're saying. We're just giving a very methodical definition of what exactly it means to say that there are n distinct elements in the set S. Because we're saying what you should do is you should take your set and then you should successively take elements away from it to find something that has cardinality 1 less, and eventually you'll end up back with the empty set, which we know has cardinality 0. So if you've had to take away n elements to do that, then that means that your cardinality was n. Well, actually, the way that the definition was set up, this particular set S has got n plus 1 elements, because we're going to have to get rid of n plus 1 elements before we're left with the empty set here, which has cardinality 0. Maybe I'll just give you an example when it's kind of maybe not so totally obvious how many elements there are in a set. So let's suppose that we take a subset of the rational numbers. So let S be a set composed of elements m over n, where m and n are integers. So that would just be the set of rational numbers. But let's suppose that we restrict m and n. So let me say that m and n are both greater than 0 and say less than 1,000,000. Okay, so that set would be finite. You've got a finite number of elements, but it's not really obvious how many it has, because the rational numbers don't have a unique way of being represented as m over n. So a half, for instance, is 1 over 2, but it's also 2 over 4 and 3 over 6 and so on. So it's not really obvious how many different distinct elements there are here. We could work it out, but in fact that's actually what this is basically saying. This is giving us a recipe for how we can work out how many elements there are in a set. It's like something that maybe a computer might be able to follow. Okay, so this set that I've just defined is finite, and it's not so obvious what its cardinality is. And to be honest, I don't know I have not worked out what the cardinality of that is. If anyone wants to work it out, you can let me know. Okay, so on the problem sheet, you're going to have to prove a proposition using this definition. So this will be a proposition. The proposition is that we let A and B be finite sets. Then the cardinality of their union is equal to the sum of their individual cardinalities minus the cardinality of their intersection. And that's maybe something that seems obvious if you think about the number of elements in the set, but it's something that on the problem sheet you're going to be asked to prove using this definition, trying to kind of systematically use a slightly awkward definition. So I'll say proof, see the problem sheet. This is always a cop-out that the lecturer says when they don't want to bother proving something themselves. Okay, but so what I'm going to do is to show you a sort of similar kind of proof of a proposition, but a different proposition. So this is going to be a proposition to do with the number of subsets of a finite set. So this will be subsets of a finite set. Okay, so I'm going to let A be a finite set with cardinality n, and then the proposition is that the cardinality of its power set is 2 to the n. I've just managed to fit that on. So if you remember that the power set is the set of all subsets of A, and so the cardinality of the power set is the number of subsets of A. Okay, and there is quite an easy way to see this. If you think about how you produce a subset of A, if A has got n elements, then you could go through each of the n elements and decide whether you're going to put it in the subset or not. So that's like a binary choice for each element of whether you put it in or not. And if there's n elements, that gives you 2 to the n different choices for whether to put the elements in or out. And that's going to give you all of the subsets, and there will be different subsets. But I want to try and show this just following the definition that we just gave of what the cardinality is. And I'm also going to make use of the proposition that we just wrote down as well. Because the definition is recursive, it's going to be natural to try and do this by induction. So this is the proof, and I'm going to say we use induction. That's the introduction to explain what we're doing. And so we're going to start with n equals 0, obviously. So if n is 0, then, well, the only set that has cardinality 0, according to that definition, is the empty set. So if n is 0, then A must be the empty set. And what is the power set of the empty set? The power set of the empty set is the empty set itself. That's the only subset. Remember that the power set is a set of subsets, so we write that like that. And that has cardinality 1, because we can get rid of the one element and then we're left with the empty set. So this set itself is not empty, but if we get rid of the one element that's inside it, then it will be empty. And if, according to the definition, that means that this has cardinality 1. So the cardinality of the power set of the empty set is 1, which is 2 to the power 0, which is what it needed to be. So the proposition is true for n equals 0. Okay, so then we're going to suppose that it holds for n. So we'll say, suppose the result holds for n. And then we're going to consider a set that has cardinality n plus 1 and try and show that it holds for that. And so then we're going to let A have cardinality n plus 1. So we want to try and show that the cardinality of the power set of A is 2 to the n plus 1. Okay. So the definition, if we follow the definition of what it meant to say that A has got cardinality n plus 1, that means that we can find some element within A such that if we get rid of that element, then we have something that has cardinality n. So I'm going to say, then there exists some, I'll call it little a, in A, such that if we get rid of little a, so that's going to be A, but having got rid of the set containing little a, and I'm going to refer to this set quite a lot, so I'm going to give that a name, so I'm going to call that A primed. that's the set having got rid of little a. That has cardinality n. Okay, and so if that has cardinality n, then that's small enough such that we're supposing the result holds for that. So we know that the cardinality of the power set of this A primed is going to be 2 to the n, and we're going to make use of that. We want to know about the cardinality of the power set of A, so we need to think about the subsets of A. So the subsets of A, either they're going to contain this particular element, little a, that we got rid of, or they're not. And if they don't, then those subsets are just going to be subsets of A primed. Okay, which are all obviously subsets of A. If they do contain the element little a, then they're basically going to be the same. They're going to be the subsets of A primed, but then having put the element little a back in again. So this allows us to build what we call a partition of the power set of A. I'm going to talk about partitions in the next lecture, but I'll explain what I mean by actually just writing it out. So we're going to split the power set of A, that's the set of all subsets, into those that contain the little a and those that don't. So let me write some explanation of that. I'm going to say that any subset of A either contains little a or not. So we can write, and this expression is going to be a bit long, so I'll write it on the next line. We can write the power set of A as the union of two sets. One of them will just be the power set of A primed. That's the set of all subsets of A primed. And then the other one, so we're going to take the union of that with the other ones, which is the set of all subsets of A primed combined with the element little a. So it's going to be a little bit awkward to write that out. So I'm going to write this as a set. I'll just write it out and then explain it. So it's going to be a set of S union little a such that S is in the power set of A primed. So if you just read that, hopefully that makes sense. So this is the set of all sets that are made up of a subset of A primed combined with the element little a. Okay, and so that's all the possible subsets of A. So that's the power set of A. And notice that these two sets that we've split it up into are disjoint, because these ones don't contain A and these ones do contain, these ones don't contain the little a, these ones do contain little a. So there's no overlap between them. So these are disjoint. That means, according to the previous proposition, which is what you're proving on the problem sheet, that the cardinality of this thing is just the sum of the cardinality of this thing and the cardinality of this thing. But both of those are the same as the cardinality of this, because the number of elements in this set here is just the same as the number of elements in this power set. And we know both of those from the inductive hypothesis are 2 to the n. So what I'm going to write here is that these two sets are disjoint, and each has cardinality given by the cardinality of the power set of A primed, which is 2 to the n by the inductive hypothesis. Hence, the cardinality of the power set of A was just the sum of those two. That's 2 to the n plus 2 to the n, which is 2 to the n plus 1, which is what we were trying to show. So I can write a concluding statement here. By induction, the result holds for all n. So if we have n elements in the set, then the number of subsets of that set is 2 to the n. Okay, let me close by just saying a word about the cardinality of infinite sets. This is something that we can say a bit more about once we have the idea of a bijection, and it's something that you will say more about in your analysis course later this term. So let me just make a comment. For infinite sets, it's much more interesting for infinite sets, but a bit confusing, because this is really getting at different sizes of infinity. I want to just make the observation that the set of natural numbers are a subset of the set of integers, which is a subset of the set of rationals, and that's a subset of the set of reals. So in some sense, these sets must be kind of larger than or equal to the previous one. And I still find this really weird. In some sense, it seems like the set of natural numbers has got to be smaller than the set of rationals. It seems like there are fewer of them. But of course, there's infinitely many of both of them. So our intuition fails us in making any kind of statement like that. And it turns out that in terms of the cardinality of these sets, that's not true. The cardinality of the natural numbers, the integers, and the rationals is the same. So they're all, in some sense, the same size sets. The cardinality of the real numbers is larger. So anything that has the same cardinality as the natural numbers is called a countable set. And if it's larger than that, then it's called uncountable. So I'll just say here, but the cardinality of the natural numbers is the same as the cardinality of the integers, and that's the same as the cardinality of the rationals, but that's less than the cardinality of the reals. But these things are all infinite cardinals, which is something that I'm not going to go into. Okay, but you will talk a bit more about this in the analysis course. Okay, so let me just summarize what we've done there. So we've seen truth tables as a way of proving set identities. We've given a recursive definition of the cardinality for a finite set, and then we've used that to prove the number of subsets of a finite set.